Okay, first of all, I would like to thank the organizers for making this event possible, also for giving me the opportunity to speak. It's been a great pleasure and honor to be here. And well, let me start my talk by presenting the main characters, and then I'll explain the problem that I will consider. So throughout the talk, K will be a number field. And A will denote an abelian variety defined over this number field. Of dimension at least 1, which I will call G. And for a prime B in the ring of integers of K, of good reduction for A, I will denote by A sub P the reduction of A modulo this prime. So this is an abelian variety defined over the residue field of K at P. K of P, okay, modulo this prime P. And I will be speaking about a local global principle. And in this context, what this means, so it refers to some global property of the abelian variety defined over the number field that can be recovered from the analogous property of its reductions for a certain amount of these reductions. So in fact, in this talk, it will not be a property of the abelian variety itself. I will always be considering, in fact, two abelian varieties, A and A prime, two abelian varieties. And more precisely, I'll be interested in the homomorphisms between these two abelian varieties and whether certain shapes of these homomorphisms can be recovered from the shape of the homomorphisms between the reductions. So maybe in this context, the most paradigmatic example is Falting's isogeny theorem. And before recalling it, let me fix some non-standard notation and terminology that I'll be using throughout the talk. So I will usually say that some property holds for almost every prime. And by this, I will write this to denote this. And more precisely, what I'll mean is that this property holds for all primes P of good reduction, both for A and A prime. And I will always, I won't care if I exclude some density 0 set. So I will ask that this holds for some density 1 set. Okay, so let me recall Falting's isogeny theorem. So imagine that your two given abelian varieties A and A prime are isogynous in the sense that so there exists a homomorphism from A to A prime, which is surjective and has finite kernel. So this means that there exists one such homomorphism with this property, and at almost all primes, you will be able to reduce this homomorphism, and it will tell you that that the reductions of A and A prime modulo P are also isogynous. And yeah, Falting's theorem, what tells you is that in fact, the converse of this implication is also true. And what's the map of the proof of this fact? Well, you need to think in terms of Galois representations. So these early days, the previous days, we've seen the Elliptic representation attached to an elliptic curve. We can also attach an Elliptic representation to an abelian variety, which I will denote by rho sub L, rho A sub L. So L will be some prime, take some prime. And so this is a representation of the absolute Galois group of K that encodes the action of the absolute Galois group on the Tate module of A, defined in the same way as for elliptic curves, the projective limit of the L to the n torsion. And now the Tate module has a structure of a QL vector space of dimension twice the dimension of the abelian variety. And what Falting showed is that A and A prime are isogynous, even only if the Elliptic representations attached to A and A prime are isomorphic. Okay, so similarly, on this side, so there's some things. We have a theorem of Tate that tells us that two abelian varieties over a finite field will be isogynous if the characteristic polynomials of Frobenius coincide. So let me denote by sub A sub B, the characteristic polynomial of Frobenius. This is a polynomial with coefficients in QL in principle, but in fact, it has rational coefficients which are independent of the choice of the prime L. And Tate tells us that AP and AP prime will be isogynous even only if these if they're the characteristic polynomials of Frobenius for A and A prime coincide. Okay. And well, of course, you have an implication down here from left to right. But now the Brouwer-Nesbit theorem tells us that you can, the converse implication also holds. If you want, thanks to the fact that these two representations are continuous and semi-simple, and then you invoke the Chebotaryov density theorem. So that's how you go from right to left. And well, the next thing I want to do is to speak about a geometric version of this theorem. And by geometric, what do I mean? Well, take now the base changes of A and A prime to an algebraic closure of K. So I'll denote by A bar the base change of A to K bar. And suppose that they are isogynous. Then the same argument as before, by reducing the isogeny defined over K bar, which is in fact defined over some finite extension of K, tells us that the base changes to an algebraic closure of the residue field at P of A and A prime will also be isogynous for almost every prime P. And well, it's, yeah. And recently, Kare and Larsen showed that, again, you can revert this implication. Okay, and maybe I should state here that this is a simplified version of their theorem. Because in their theorem, they show that you can replace the property of being isogynous on both sides by the property of sharing a common isogeny factor, which makes the problem more complicated. And they also specify a density of primes such that if this condition on the right holds for a set of primes of that density, then the converse implication will already hold. You don't need to ask it for a set of primes of density 1. Okay, so with that said, well, it is natural to ask whether a property of an isogeny, certain property of an isogeny can be read from the corresponding property of the reductions. And the property I'll be interested in this talk is the property of this isogeny being a quadratic twist. So let me explain precisely what I mean by a quadratic twist. So I will work in the category of abelian varieties up to isogeny. And well, this is the category where the objects are abelian varieties, but the morphisms between objects are the usual homomorphisms between abelian varieties tensor with Q, in such a way that in this category, the isogenies, which in principle have a non-trivial kernel, become invertible. And good, so so let me make some precisions here. So we want to make a definition that is valid both for A and its reductions. So let B be an abelian variety over some field F, where this F is either the number field K or some residue field. And so in this category, when I speak of the endomorphisms of B, which I will denote this way, putting a 0 here, what I'm referring to is in fact to the usual endomorphisms of B tensored with Q. So that this becomes a Q algebra. And thanks to this consideration that I'm doing, I can make use of the following terminology. I will say that another abelian variety, B prime over F, is a twist of B. So whenever I say this, what I really mean is that B and B prime are geometrically isogenous. In other words, their base changes to an algebraic closure of F are isogenous. So that's what I will mean by twist in this talk. And now I need to tell you what I mean by quadratic twist. And for this, let me recall that, that there is the following map. Consider the set of twists of B. Then define a map to H1 of the absolute Galois group of F, acting on the geometric endomorphism algebra of B. Or rather on its invertible elements. And what is this map? Well, you give me a twist B prime of B. So this is an isogeny between the base changes. And on this side, I consider the one cocycle that sends some element sigma in GF to the compositum of the inverse of the isogeny. And then I come back by twisting by sigma. So I call you in this category, I can invert isogenies. And then, so this is the map defined by the map that sends this twist to the cohomology class of this one cocycle. And then in this category of abelian varieties up to isogeny, there's a theory of Weil descent that tells you that this map is in fact a bijection. Good. So the next thing I want to do is, well, observe that inside this, this geometric endomorphism algebra, well, I can find plus and minus the identity. And this injection in here induces a map of cohomology spaces. H1, GF in here. Let me call this map iota. And then I will say that a twist B prime of B is quadratic if it lies in the image of iota. So that's what I mean by quadratic twist. So of course, this in here, the action is trivial on plus minus one. So these are just homomorphisms from GF to plus minus one. So this space is just the space of quadratic characters. And to any quadratic character, I can attach a twist. Well, this cohomological interpretation will be useful later. But if you want a more explicit one, well, here is a remark. So let's go back to our abelian varieties A and A prime defined over the number field K. We say that, the fact that these two abelian varieties are quadratic twists of each other and just means that their corresponding Elliptic representations differ by multiplication by some quadratic character. This you can get from Falting's isogeny theorem. And what it means that reductions AP and AP prime are quadratic twists. Well, it's again some easy exercise to see that this just means that the polynomial of Frobenius at P of A prime can be recovered from that of A relative to A, well, it will either be equal or it is obtained from it by negating all the roots. So these reductions are quadratic twist will amount to say that these equality holds. Yeah. Is there any question so far? So not, then having introduced all the notions that appeared in the title, I can already state the main theorem I want to talk about in this talk, which is the following. Well, if you look at the characterization at the end of the blackboard, you'll see that clearly, if A and A prime are quadratic twists, then it's almost every prime, the reductions will also be quadratic twists. And well, the theorem that I want to present today states that up to dimension 3, then the converse also holds. Okay. So yeah, let me make one remark here. So I'll introduce another piece of terminology. Yeah, yes. Yeah, all the time from now on. So if this condition on the right holds, I will simply say that A and A prime are locally quadratic twists. So, sort of terminology description. And well, let me just say that, give another description of this fact. Maybe if you have a more automorphic mentality, you'll prefer to think about this problem in this way, saying, so this is, in geometrical terms, it's some property of the reductions, but some problem that is local in nature, but you can think about it globally too. So this just means that the tensor squares of the Aladic representations of A and A prime coincide. That the exterior power, if exterior powers for I odd, so or for I even also are isomorphic. And in the I odd case, the condition you need to put, well, you'll have that these exterior powers will be isomorphic after tensoring with rho and relative to A and A prime on each side. So after doing this operation. Okay, that's just looking at the effect on the characteristic polynomial of the change of the sign in the variable. So you can think of this local global principle as a problem for, so as an equation of representations, and it asks whether the solution is unique up to quadratic twist. So the second remark that I want to make is that this theorem is known if G is 1. It was known if G is 1. Thanks to the works of Professor Rajan and Ramakrishnan. And it's not the joint work. These are two different theorems, and in fact, they're very different from each other. In fact, so Ramakrishnan's theorem is genuine to representations of degree 2, and it's purely group theoretic. And Rajan's theorem is of a more Aladic nature, but it's in general dimension. And in fact, so they're very different, but a common feature that they both have is that the proofs are very beautiful, and I really encourage you to go and look at them. Another common feature they have is that they play a very important role in the proof of this theorem in higher dimension. So I think I won't have time to explain the role of Ramakrishnan's theorem, but it plays a determinant role in the case that your abelian variety is isotypic, in the sense that it's geometrically isogenous to the power of an elliptic curve. And Rajan's theorem, I'll come back to it later. Before doing so, though, I want to give an example. Which is due to Edgar Costa. It's the following one. So you take abelian varieties, your field of definition will be Q, and you let A be the Jacobian of the genus 4 curve, y squared equals x to the 9 plus x, and you let A prime to be the Jacobian of the curve C prime equals y squared equals x to the 9 plus 16x. So these are four-dimensional abelian varieties, and they violate the local global principle. And I'd like to explain to you why they violate the principle. And so these examples were found in a computational way by Edgar Costa, but I gave a talk in Lumini last spring, and Alex Smith was in the audience, and he pointed out to me a very simple and nice proof of this that I want to show to you. So if you're familiar with the counterexample of Wang in the original formulation of the Grunwald-Wang theorem, I think this will be very reminiscent, because the proof that this is a counterexample goes in the following way. So first thing we have to show is that they are locally quadratic twists. Why is this true? Well, take the following numbers. So let B1 be the square root of 2, B2 be the square root of -2, and B3 be the B1 plus the square root of -1. And what these numbers have in common is that they are 8th roots of 16. And well, maybe you already see how the proof will go, because 16 is this rational number with the property that not having a rational 8th root, modulo p for every odd p has an 8th root defined over fp. And so now what I claim is that the map pi from C to C prime, or maybe from the base changes of C to C prime to an algebraic closure that sends the point xy to the point beta ix, beta I to the 9/2 y, is an isomorphism. This is a very simple calculation. And now, well, I claim that, in fact, for every odd p, the reduction mod p of sum of one of the phi sub i's is defined it defines a quadratic twist. If you want, in the usual sense of quadratic twist, it's after a base, so it will give an isomorphism defined over fp squared, but on the Jacobian it induces an isogeny between the respective Jacobians. It induces an isogeny, which is a quadratic twist. And the reason is very simple. So the reason is that modulo p, sum of these numbers, is defined over fp because the product of these Legendre symbols is 1. So not all of them at the same time can be -1. Good. So this proves that these abelian fourfolds are locally quadratic twists. How do you show that they are not quadratic twists? Globally over Q. Not quadratic twist. Well, the first thing you do is to observe that A and A prime have good reduction outside 2. And well, there's the theorem of Silverberg that tells you that the homomorphisms between two abelian varieties are defined over some extension that can only, that is unramified at the primes of good reduction. So this means that to rule out that they are quadratic twists, it is enough to check that they are not quadratic twists. Over the quadratic fields that are unramified outside 2. So they're not quadratic twists over Q beta I, Q beta 1, Q beta 2, Q beta 3, and this you can do it by looking at characteristic polynomials of Frobenius. Okay. So having done these remarks, I would like to give some ideas of the proof of the theorem. Is absolutely reducible. I don't know. We are working on this. If the geometric endomorphism ring is just Z, if there are only the Z multiplications, then it is true. And yeah, I'll explain how this follows from your theorem. But in the case that the abelian varieties are absolutely reducible, we're working on this, and that's really, yeah. So it will be mentioned now because I want to give you some ideas of the proof. So I say many times the proof of a theorem, which is a wrong thing because all one can say is that there is a proof. And this pedantic comment today is very relevant because, in fact, I will not explain the proof that was written in the published article. I will explain some sort of new proof that we are working out in collaboration with Emiliano Ambrosi on some ongoing project. Okay, so before I can explain the main steps in the proof, I need to introduce some very important notion, which is the field K connected. So let me define a couple of things. So now I'll take rho to be a representation obtained from the L-adic representation attached to A by linear algebra. So if you don't like this vague statement, here you can, I'll just be interested in what I'll be saying from now on. I'll be interested in the case when this rho is either the L-adic representation or its tensor square. Okay, so you can just think that rho has these two possibilities. And I'll denote by GL the L-adic monodromy group attached to rho. And this is the Zariski closure of the image of rho. It's some algebraic group over QL. And I'll denote by K connected the minimal extension of K at which this L-adic monodromy group becomes connected. So the minimal, and here I'm making a proper use of the article the. Minimal L over K such that the Ladic monodromy group relative to the restriction of rho at GL is connected. So Serre showed that this extension is independent of the choice of the prime L by means of some characterization of this field that I want to recall, because it will play an important role later on. Before doing so, though, yeah, let me just comment that I will simply write case of A con in the case that rho is the Ladic representation attached to A. And well, I'd like to give you some insight on this extension. Maybe the first thing that I can comment is that this field always contains the field of definition of the endomorphisms of A. So in other words, the minimal extension L over K over which the abelian variety attains all of its geometric endomorphisms. And in fact, by work of Kiran Kedlaya and Grzegorz Banaszak, building on the work of many others, we in fact have equality if the dimension is at most 3. Okay, so this gives some insight. But now what I want to do is to recall Serre's characterization of this extension. That appeared in a letter to Ken Ribet of the 1st of January, 1981. And it's the following one. So Serre describes this field. Yes? No, there are these counterexamples of Mumford already in dimension 4. And yeah, Davide has a very nice article, in fact, where he found very explicit counterexamples as Jacobians of curves. And yeah, so Serre looks at this field in the following way: as the minimal extension L of K with the following property. So take some prime in the ring of integers of L and look at the subgroup generated by the Frobenius eigenvalues. So right, these eigenvalues belong to Q bar because we said that this is a characteristic polynomial of this matrix has coefficients in Q. I will denote this group by gamma rho P, so it's some subgroup of Q bar star. And then look at the set of primes P for which this subgroup is torsion free. then IISER characterizes K connected as the minimal field for which this set has density 1. So maybe now you can think of the example of an elliptic curve with complex multiplication. Well, in this case, Kcon and Kn have to coincide. We know that the endomorphisms of an elliptic curve with Cm over Q are defined over the field by which the elliptic curve has complex multiplication. But if you play with the Frobenius eigenvalues for the primes, which are inert in the quadratic imaginary field, you'll get again that K connected is this imaginary quadratic field. Okay. So with that said, I can give the main steps of the proof of the theorem that I raised there, the main theorem. They are the following. So there are 4 steps. Step 1 is, well, you show that if the tensor squares of the L-adic representations of A and A prime are isomorphic, then the geometry of A and A prime is very much related. So on the one hand, you have that A and A prime have to be twists of each other in the sense that with the meaning that we are giving to the word twist in this talk, they are geometrically isogynous. And second, K connected for A and A prime coincides. So now on, maybe I'll just call this field, call and write just K connected for this field. And good, what's the second step? The second step in the proof is to show that if A and A prime are locally quadratic twists, and their L-adic monodromy groups are connected. In other words, K connected coincides with the field of definition K. Then the abelian varieties are quadratic twists of each other. The third step is so imagine that, well, maybe I should say that so these steps are independent of the dimension. And from now on, I restrict to dimension at most 3. So, and you restrict to dimension up to 3. And then step 3 consists in showing that, well, if you know that that your abelian varieties are quadratic twists, maybe over the minimal field where the endomorphisms are defined, then already they had to be quadratic twists of each other over the field of definition. And now with all what I have said, the concatenation of these steps proves the theorem, because, well, if the abelian varieties are locally quadratic twists, then in particular, the tensor squares of their representations will be isomorphic. So you will have this, that these two things will hold. And well, just to make sense of step 2, I'm using the second part, the fact that A and A prime are twists plays a big role in the proof. And then, well, you use that K connected coincides with the minimal field of definition of the endomorphisms up to dimension 3, and you apply step 3. But I had said that there were 4 steps, and that's because that's not entirely true. Doing this reduction, descending the quadratic twist from Kn to K, it becomes a difficult task if A is isotypic. So you have to ask that in here that A is non-isotypic. Remember, by isotypic, I meant an abelian variety that is geometrically isogynous to the power of an elliptic curve. And then, so step 4 consists in giving a direct proof. In the case that A is isotypic. And it is in this step 4 that I'll not have time to tell much more, that you reuse Ramakrishnan's theorem in a quite unexpected way for me at the beginning. You express the Tate module of an isotypic abelian variety as the tensor product of an aladic representation of degree 2, which is sort of associated to the elliptic curve factor, and an Artin representation of degree now G. And this reduction in the dimension by 2, it's what allows you to when you consider abelian surfaces with representations of degree 4, to reuse Ramakrishnan's theorem for the Artin representation. Okay. So that's the plan of the proof, and I'd like to give some ideas on the first 2 steps. Yeah, I have some time. So yeah, is there any question on so far? So step 1. And well, in this case, so step 1 directly follows from the work of Professor Rajan. I will state this theorem again in a simplified way, the one we need in our context. It has the following 2 requirements. So suppose that the aladic monodromy group is connected. And then look at the set of primes at which the Frobenius traces of the aladic representations attached to A and A prime coincide. Then if the upper density of this set is positive, then one has that the aladic representations are potentially isomorphic, which translated via Falting's isogeny theorem means that A and A prime are twists of each other. Maybe just a few words on why we can apply the theorem in our situation. Well, if our abelian varieties are locally quadratic twists, in particular, their Frobenius traces just differ by sign. And then the only way that this condition might fail is if for a density 1 set of primes, the trace of one representation was precisely minus the trace of the other representation, which by Chebotarev would mean that the trace of a character of one representation is minus the character of the other one. It certainly cannot happen if you look at the trace at the neutral element of the group. And this property is preserved after a base change. And so we just want to prove that A and A prime are twists. And so we are free to assume that the L-adic monodromy group is connected. So maybe I should say that the first part of step 1 follows from this theorem. Yes? That such an L exists. Well, yeah, it's part of the of Searle's theorem. That. Well, I mean, the eigenvalues will differ by roots of unity, and you can bound the order of these roots of unity in terms of the dimension of the abelian variety, and then there has to exist some extension at which you kill all the roots of unity. But I keep this on the board because now I want to. Oh, maybe okay. I have to erase something, but I wanted to keep step 2, step 1. So why does the second part of step 1 hold? Well, it directly follows from the fact that K connected for A coincides with K connected relative to the tensor product of A, of the L-adic representation attached to A, and its contragradient. And well, before explaining to you why this equality holds, well, let me just comment why this implies this part. Well, this is simply because the contragradient of rho is isomorphic to rho Tate-twisted. So you just Tate-twist your hypothesis, and then you have that these two fields coincide for A and A prime, and so does this field. And how do you prove this? Well, now we're going to use Searle's result that I kept there. What you do is you consider a torsion relation between the eigenvalues of Frobenius. So consider some product of this form. Where these pi j's are integers, zeta is some root of unity, and the alpha j's are the eigenvalues of Frobenius. Now I'll do a beautiful trick. I'll just rewrite this in a more convenient way. I want these exponents are integers. I want them to be non-negative. And then if I want this, all I have to do is to divide by alpha j to the nj. And now I can assume that nj and pj are non-negative. And once I have this, well, now take some embedding of this into C and take the absolute value, because these are real numbers of weight 1. When you do this, what you see is that the sum of the EJs has to equal the sum of the NJs. But this means that you can pair any alpha in the numerator with an alpha in the denominator. So, and since the quotient of two such Frobenius eigenvalues are precisely the Frobenius eigenvalues of row tensor its contragradient, you can just regard this torsion relation between eigenvalues of row A tensor contragradient, and then Serre's theorem just renders this equality a tautology. Good. And then in the remaining minutes that I have left, yeah, is there any question about this argument? Okay, so in the minutes that I have left, I'd like to give a sketch of the proof of step 2. Okay, so now we will make use of the cohomological description of the twist. So by step 1, we have that A prime is a twist of A. So A prime defines some class in H1 of GK with values in the invertible elements of the geometric endomorphism algebra, right? But now I'll find some class in here, but I'll look at the image of this class in the cohomology space having coefficients in this quotient. So, and I'll call the class that A prime defines by C prime. Why I'm doing this? Well, I want to see that A prime, it's not just a twist, it's a quadratic twist. So I want to see that it is trivial in this H1. Well, and to do this, I do the following. I pick some prime of good reduction, and then one has that there's a well-defined map into the H1 of the absolute Galois group of the residue field at P with values in the vertical elements of the geometric endomorphism algebra of the reduction of A modulo P. Okay, and in fact, well, I can do this for many primes, right? And I'll do this for every prime in a certain set that I will now define. And well, so this is a set that consists of primes that are, well, I need that they are of good reduction so that this is well defined. Then I will further impose that the reductions of A and A prime at P are quadratic twists. I know that this happens for a set of density 1 primes. And I will further impose that that group that I had defined there, the subgroup generated by eigenvalues of Frobenius, is torsion-free. Okay. So, well, what do I get? If I look at this map, which I will call, let me call it phi. If I look at the image by this map of this cohomology class, well, this has to be trivial. And that's because I'm assuming that that for every prime in sigma, sorry, I need to, need to mod by ±1 here, sorry. So that the image is trivial just means that the reductions are quadratic twists at that prime. But so if now what I need to do to show that A prime is a quadratic twist is that to show that the map phi is injective. But why is this map phi injective? Well, in step 2, we are assuming that K connected is K. So in particular, all the endomorphisms are defined over K. So this H1 is just some humps. And then you use the fact, it's some easy exercise, that the group generated by Frobenius eigenvalues is torsion free to show that all the endomorphisms of the reduction of A modulo P are also defined over the residue field at P. So these are again ohms. So if you look at the kernel of phi, you'll have some homomorphism that vanishes on every Frobenius in this set sigma. But this set sigma has density 1 by hypothesis. So this tells you that phi is injective, and this concludes the proof. And maybe I could add that for step 3, just in words, that it's something we're working on, but then the proof really depends on the possibilities that you have for the endomorphism algebra of A. And we believe we're trying to prove that in general, if A is absolutely irreducible, then this local global principle might hold in general. But we're not completely done with this. So step 4, I already said some words about it. So I'd like to stop here and thank you for your attention.
Francesc, for a nice talk. Are there any questions?
Yes.
In the counterexample by Costa, do you know if the two abelian varieties or the two Jacobians are twist over Q2? Or quadratic twist over Q2?
Oh, I don't know. I didn't look at. Yeah.
Okay, and then
I think there is a parallel story of all these. You could consider the analogous problem over the completions of Q at different primes, and I'm not entirely sure that that the problems are equivalent.
Okay, thank you.
Further questions?
I might have missed it, but do you think there could be a more general criterion for your arguments in some cases for higher dimension, assuming some more properties than the abelian varieties?
Yes, I think so. And in fact, I'm not even sure in which dimensions this local principle holds true. You can easily construct a counterexample in dimension 6, but for example in dimension 5, I don't know if the local global principle holds or not. I don't know. But it is true that, for example, for isotypic abelian varieties, in this sense that they're geometrically isogynous to the power of an elliptic curve, then then you can prove it when the dimension is odd, for example. And I think there's still work to do, especially in this case that the abelian variety is geometrically irreducible when the endomorphism algebra is It's a division algebra. Yeah, maybe I should have said that in this example in dimension 4. In that case, the abelian fourfold is isogynous to the square of an abelian surface with complex multiplication. So these are complex multiplication abelian varieties of non-primitive type.
Okay, thank you.
Now here you want density of one set, but can we make it less than one and still make the argument work?
Yeah, good question. I think that when the principle holds, it should be enough to require it for a set of density bigger than the size. So that essentially the number of connected components of the aladic monodromy group should work. And so some density is strictly larger than this. And yeah, but I don't know if this is a sharp bound in the sense that I don't have examples in dimension 2 or 3 for which violate the principle. But for this density, they are locally quadratic.
It's a vague question about the counterexample. You mentioned the connection to Wang's counterexample to Grunwald's theorem. And so, I mean, how deep is the connection between the two? Because I recall well, Wang's counterexample is essentially the only counterexample, or something like that. And so I wonder if there are more counterexamples in the situation you consider, or is it all derived from that?
Yeah, I think that's very interesting, but it's difficult. The way this arises a posteriori, the parallelism is clear, but in the way you would construct the curves, there seems to be something that is genuine to dimension divisible by 4. Because you could use this property of 16 for other genus, but you don't seem to be able to construct the curves. And so yeah, I don't know, and it'd be very nice if somebody can figure it out. Oh, I don't. In that case, it's a Galois group of order 16. Yes.